So in the United States, we have 60 hertz AC power. What that means is our AC current looks like this on an oscilloscope. This being 0, this being plus DC, this being minus DC below the zero cross, and we have an alternating current. This happens 60 times a second in the United States, and in Europe this happens 50 times a second. That's the difference between 50 and 60 hertz power. What's important to note about this sine wave is that every time the voltage crosses the zero line, it creates what we call a sync pulse. This sync pulse occurs 60 times a second. At each sync pulse, a burst of signal is sent out of the command base through the halo that is transmitting out of both outside rails on the track and being received by the signal or by the antenna inside your locomotive. Now inside your locomotive, the receiver is connected to the chassis, which we'll draw as ground, and the other side, the hot, goes to the collectors that roll along the center rail. The center rail is AC hot, and the chassis is AC ground, or common, or return. The receiver is connected to AC hot and AC ground. So it too is looking at this sync pulse, because your transformers and your command base are all getting power from the electricity coming out of the wall. So as the command base sends a burst of signal 60 times a second, the receiver inside your locomotive, through its antenna, is synchronizing itself with the transmission of this signal and grabbing that signal 60 times a second. This is how the command receiver inside the locomotive communicates or receives its communication through the airborne radio signal that's being broadcast through the outside rails. This is very important and will become apparent very shortly. Let's talk briefly about how your command signal is broadcast throughout your railroad. The command signal, or the COM, is 455 kilohertz. It's really not important to know this, but we'll bring it up anyway. Your track consists of 3 rails, which we'll represent here. Tubular track ties these 2 rails together through the metal ties, and there's a piece of insulating paper that insulates the center rail from that tie. These 2 rails are AC ground, and the center rail is AC hot. On Line L Fast Track, even though you've got a plastic roadbed, on the underside of the track there's a metal connector that connects both outside rails together. So when you put a wire to this rail, it automatically transfers the current to this rail. The center rail is always hot, so it's not affected by these 2 rails at all. Well, when it is, you've got a short circuit. For tracks such as Atlas O, MTH, Gargraves, and any other brands out there where they have plastic or wooden ties, such as Ross Custom Switches even, these 2 rails are electrically isolated, meaning they're not connected by any piece of metal. So it's important for the command control operation that the 2 outside rails be connected. The reason it's important is because the COM, or this 455 kilohertz signal, is broadcast out of both outside rails. These circles represent that radio signal. As these signals are broadcast, you'll notice that the crosshatch up here on the track itself typically occurs about 2 inches from the top of the center rail to the strongest concentration of signal being broadcast through the air. On all of your Lionel locomotives, such as steam locomotives, the handrails function as the antennas. On your diesel locomotives with plastic shells, you have a metal antenna right underneath the roof of the plastic diesel. The reason this is important to know is because we need to talk about signal interference. This signal on this drawing represents 60 pulses of signal per second. Our track is being powered by our transformer. So we'll draw our transformer here is powering our track. Our command base is putting the signal on the AC ground or outside rails of both rails. This wire has absolutely no polarity. It's not hot and it's not ground when it's disconnected. It becomes ground because it's tied to the outside rails, which are AC ground for the track power. Now, this transformer is sending out an AC waveform that's generating a sync pulse for our receiver to expect a command signal at each one of these intervals, 60 times a second. Our base is broadcasting this signal that aligns itself with the antenna and therefore the receiver inside the locomotive to pick up that signal. What happens when you don't have 60 pulses of signal per second is you end up having too much signal as opposed to not enough. A great example of this is when you've got a track on the top and a track on the bottom, both being run in command mode. And when the train goes under or goes over that area, the headlights on the locomotive begin to flicker. Sometimes the engine will drop into conventional and take off at full speed. Sometimes it'll stop, sit there and flicker the headlight waiting for a command. The reason this occurs is because your command signal is actually overlapping one another. So instead of having, if we can show here representatively, this is, say, track 1. And these dashes represent that sync pulse on the AC waveform on the track. It also represents the sync pulse coming, or the command signal coming out of the base on that sync pulse. So 60 pulses per second. If track 2 is out of sync on that AC waveform by just 1 millisecond, what ends up happening is your sync pulse is off. So what your locomotive sees in that area is 120 pulses of signal per second instead of 60 pulses, because it's just out of time by 1 millisecond. This variable goes up by 60 as you increase the number of tracks and the potential for that sync pulse to become out of sync. The out of syncing happens because, say, track 1 is 100 feet long and track 2 is 75 feet long, and the transformers are connected at the same place at the start. At some point, track 1 will be out of sync with track 2. This most commonly occurs where you have an area such as a tunnel or a bridge. Let's assume we have a track here that goes through a tunnel, and we have another track here. going through the tunnel. What will end up happening is this is the upper track and this is the lower track. What ends up happening is in this area right here, we have 120 pulses per second of signal. So anything that goes under the upper track will be affected. Anything that goes over the upper track will be affected. The great thing is we have a way to solve this. And it's very simple. It's called a ground plane. Effectively what a ground plane is, for lack of a better word, is it's a force field. I can give you a perfect example. If we take a section of track that is 8 feet long, assuming that this is 8 feet, and we take a command base here, and we take a command base here, and we connect it to the outside rails, what ends up happening is we have no signal because they're canceling each other out. So we can take a large piece of aluminum foil, metal, brass, copper, anything that is conductive metal, and we can place it over top of the track right here in the middle. That piece of conductive metal gets connected to earth ground. And all earth ground is that third prong on your electrical outlet. This one here. Earth ground tied to this metal shield effectively stops all of this signal and kicks it back. Earth ground does not allow the signal from this base to exceed this plane. It does not allow the signal from this base to exceed this plane. So what we have is we have perfect command control here and perfect command control here, so long as that ground plane is separating those two signals. Take the ground plane away, suddenly the locomotives will drop into conventional mode because the two command signals will cancel each other out. If we take away this base, we can take away this ground plane. Signal interference, or I should say the crosstalk of signals, like I said, they happen in 60 pulse intervals. So they go up by a multiplier of 60. You have one track here that's seeing 60 pulses per second. And it's clean. And let's assume that this is 100 feet long. We have another track here, and we'll assume that it too is 100 feet long. And it has 60 pulses per second of signal coming through it. We have yet another track, and it's 75 feet long. And I'm simply making these lengths up. Your particular railroad will vary. Every railroad does. And then finally we have another section of track, or another line of track. And we'll say this one is 60 feet long. Now what we should have, and what we do have, is 60 pulses per second on each track. And that command signal is broadcasting out of both outside rails on all these tracks. Because of our distances, or because of the environmentals of our railroad, we could potentially have, in this area here, 120 pulses per second. Same thing here. Could be 120, could be 180 pulses per second. This area could be 120, 180, could even be 240. And over here we've got roughly 60 pulses per second. So what ends up happening in this area is whenever you run a train through any of these tracks, you could have a potential where the headlights flicker and the engine loses its command signal. This happens because of this crosstalk of the signal. It's very rarely, if ever, an instance of not having enough signal, but rather having too much signal. And the way to solve these problems is with that ground plane. And in an instance such as this, where we have 4 parallel tracks, the easiest way to solve that with a ground plane is as follows. We have, I'm just going to show you 2 tracks. My arms aren't long enough. We have 2 parallel tracks. How do we solve 120 pulses of signal in this area here? We simply take a wire. It can be anything from a 30 gauge wire to a 1 gauge wire with insulation on it. It doesn't matter if it's stranded or solid, copper, metal, I don't care. It just has to be a wire with insulation around it. And lay it between the 2 tracks. This wire gets connected to earth ground. With this in place, what we're doing is we're effectively making a force field that keeps this signal on this side and this signal on that side. Yes, both command signals are being broadcast from the same base, but depending upon the wire length of the bus feeding this track and the bus feeding this track, we can have literally a matter of a millisecond causing us to have 120 pulses of signal in this area. By having this ground plane installed, or this ground wire that's functioning as a ground plane vertically, we're separating the command signal on either side. In an instance where you have an over and under scenario, such as this, and let's say we've got a track running this way, if you will, this representing the ties. In an instance like this, what we want to do is we want to make sure that our ground plane goes this way, so that we create a plane vertically, or horizontally rather, whereas when it lays between the tracks, it's creating a ground plane vertically. We want to create a ground plane horizontally. This can be done by simply taking a similar wire and stringing it back and forth underneath the sub-roadbed of the upper track. It can be aluminum tape with an adhesive backing on it that'll just simply stick to the underside of the sub-roadbed. It can be copper, it can be wire mesh. It makes no difference at all what you use. It has to be metallic, so therefore it's conductive. And we simply take a wire, attach it to it, and go to this earth ground prong on our outlet. This ground plane is the ultimate end-all be-all solution to your problems on your railroad should you encounter any crosstalk of signal, meaning you have signal interference issues on your railroad. The ground plane is a very simple solution. Just about every house in America has these earth grounded outlets on them, or in them rather. It's a very, very simple solution. I'm not saying that when you build a railroad you will have these problems, because every single layout all over the country differs and it varies. But depending upon the environmentals of your railroad, the wiring of your railroad, etc., you can have perfect command signal, or you could have a layout that has a couple of plagued areas where you have poor signal reception, or you could have several. At the end of the day, the ground plane is how you prevent that crosstalk of signal from affecting your operations on your railroad. Your command base generates a command signal. That command signal is 455 kilohertz. That signal broadcasts through both outside rails. It has no electrical current whatsoever. It's simply a radio frequency that's being broadcast through your rails themselves. So effectively your rails are acting like a vertical radio antenna laid on its side. And that signal travels through the electromagnetic field of the track. It's important to know this because both outside rails need to be tied together. If you have a layout where you have one rail that's electrically isolated for block signaling or signaling purposes, there is a way to cheat it. In order to cheat that, what you do is you use a 0.1 microfarad 50 volt ceramic capacitor. And I'll show you how this all hooks up, or all wires up. Assuming that this is your section of rail, and these gaps represent your isolated sections, what you do is you take your capacitor and you place it over the gap. One capacitor for each gap with a leg on each side. Then the other rail, up here for instance, your other outside rail, has your command base connected to it. To connect this command base wire to this insulated outside rail, you need to put yet another capacitor from the command base that goes to the grounded rail to one of the insulated rails. And basically what you're doing is you're creating a capacitive coupling that allows the 455 kilohertz to broadcast over these electrically isolated rails so that you can still achieve the command signal broadcasting from both outside rails without actually putting any current through these rails or any polarity through these rails. So your wheels of your train will still continue to activate your block signals, but yet you'll still be able to transmit your command signal through both outside rails properly. And again, that capacitor is a 0.1 microfarad 50 volt ceramic capacitor. If you have a large layout with a long insulated outside rail with several blocks, you're going to need a lot of them. These are very inexpensive components available from large electronic suppliers. A search on the internet, I'm sure, will turn up suppliers near you. But this is all that's required to get your command signal to broadcast from this insulated outside rail so that you still achieve the functionality of having both rails broadcast your command signal and still take advantage of all of your insulated outside rail detection functionality.